Hello everyone, nice to talk to you all again. Hope you are not too bored with the spring break last week. I know that it must be a quite boring week in your experiences. I know that this is not an ideal situation to learn about the contents of this course, but let's try to do our best when we're trying to go through these contents here for the rest of the semester. So I have collected all your exam 2 contents, and I'll start grading them, and hopefully I'll be able to post the scores before Friday. But just by glancing at your exams, I think you all did pretty good. So starting from this class, we're going to learn about the wastewater treatment. So if we go back or do a recap of our last section, so basically we talk about two chapters or two types of contents, right? So we talked about the water quality, and in water quality we specifically mentioned about the new idea or new concept, which is the biochemical oxygen demand, which is the oxygen that's demanded by the microorganisms in the water to oxidize all of the organic components. So we also mentioned about the NBOD, which is the nitrogenous BOD. And we mentioned about the concepts for the dissolved oxygen, which is DO, oxygen deficit. And we use the oxygen deficit, or the OD, to solve for the DO sag curve, right? And further, in terms of the water treatment, although it did not specifically mention about this definition, so basically for the water treatment, we're trying to solve for we're trying to deal with the drinking water treatment system. And starting from this class here, we're going to talk about the wastewater treatment. So for the drinking water treatment, we learned about the basic processes such as the coagulation, flocculation, and clarification, right? We talk about the softening, which is mainly dealing with the hardness of the water. And then we learned about the sedimentation, which is using the gravity of the suspended particles or the heavy particles to remove those contaminants in the water. We learned about the filtration and also the disinfection at the end, okay? So as you can see later from this third section of the course here, you can see that we are going to use some similar devices to purify the wastewater, all right? So why do we care about the wastewater? We know that the drinking water is vital for the human being because we all need clean water to sustain ourselves. But why don't we just dump all of those wastewater back into nature? Doesn't the nature have its capability to accommodate these wastewater? Actually, it's not. So during the process when we were trying to learn about the DO sag curve here, we actually find out that when the BOD of the sewage water is higher above certain value there, so the dissolved oxygen might get to the critical point where the dissolved oxygen concentration drop to 0. And that's going to exterminate or remove all of the living organisms in the water, which is a disaster in terms of the water quality, right? So that's why we have to treat the quality of all of these wastewater before we dump them back into the environment. So here I have a short video which is talking about how the wastewater treatment plant works. Okay, so let's all go through it here.
I knew he was spending a lot of time at the piano, but I was doubtful he could get that far with. I knew he was spending a lot of time at the piano, but
where does last night's dinner go? It's a topic. Well, you may already be grossed out just thinking about it. This question leaves vague to a significant subset. Well, you may already be grossed out just thinking about it. This question leads to a significant subset of civil engineering and a massive amount of public funding. Just like all dogs go to heaven, all drains in a city lead to a wastewater treatment plant where that wastewater gets turned back into water that we can drink. Now, nasty
You
part
may
of
be
real
thinking
life.
that you'd
But
rather
here's the
just let
thing.
bygones be
Chances are
bygones
you've
and
drunk
not
water
think
that
about
was
this nasty
waste
part
at
of
some
real
point.
life.
So you
But
might
here's
want
the
to take some
thing.
time to
Chances are
understand
you
this
drunk
engineering
water that
process
was
that makes
waste
dirty
at
water
some point.
clean.
So you might want to
Here's
take
where
some
it
time to
starts.
understand
The
this
toilet.
engineering
Once you're
process that
done
makes
doing your
dirty
business
water
and flush
clean.
that magical
Here's
handle,
where
your
it
waste
starts.
ends up at the
The
inlet
toilet.
of one
Once
pretty
you're done
interesting
doing your
place,
business and
a
flush that
wastewater
magical
treatment
handle,
plant.
your waste
Why
ends
is
up
this
at the
place so
inlet of one
interesting?
pretty
Because it
interesting
takes
place,
arguably
the
one of the most
wastewater treatment
disgusting
plant.
substances in
Why
the
is
world
this
and
place
turns
so
it back into
interesting?
something that
Because
is
it takes
essential to
arguably
all
one of the
life.
most disgusting
Flushing
substances
just
in
the
the world
toilet
and
at
turns it
halftime
back
may
into
not seem
something
like
that
a
is
big
essential
deal,
to
but when
all
you
life.
couple it with thousands,
Flushing
if not
just your
millions, of
toilet at
others doing
halftime
the
may not
same,
seem like
it
a
can
big
result
deal,
in some
but
pretty
when you
high
couple it
sewage
with
flow
thousands,
rates.
if not
New York
millions of
City has an
others
array
doing the
of
same,
14
it can
wastewater
result in
treatment
some
plants
pretty
that
high
handle a
sewage flow
combined
rates.
1.3
New York
billion
City has an
gallons of
array of
wastewater
14
daily.
wastewater
That's enough
treatment plants
wastewater
that
to fill the
handle a
Dead Sea
combined
with pure
1.3
sewage in
billion
just 8
gallons of
years.
wastewater
And
daily.
that's just
That's
New
enough
York City.
wastewater to fill the
There
Dead
are
Sea
an
with pure
estimated
sewage in just 8 years.
14,748
And that's
treatment
just
plants
New
in the
York
US
City.
alone that
There are an
76%
estimated
of the USA's population relies on,
14,748
according
treatment
to the
plants in the
American
US
Society
alone
of
that
Civil Engineers.
76% of the
Understanding
USA's
wastewater is
population
crucial
relies
to
on,
understanding
according to
the
the
critical
American Society
infrastructure
of Civil
needed to support
Engineers.
modern life.
Understanding
That brings
wastewater
us
is
to the
crucial
first step
to
of the
understanding
process
the
that
critical
handles
infrastructure needed to
larger
support
items
modern
and
life.
sewage,
That brings
things
us
like
to the
flushable
first step of the
wipes,
process that
2x4s,
handles
toys,
larger
or even
items and
guns.
sewage,
You name
things
it, and
like
it's
flushable
probably been
wipes,
caught in a bar
2x4s,
screen. Bar
toys,
screens
or
are
even
exactly
guns.
what you would
You name
think.
it, and
They
it's
are
probably
large
been
vertical
caught
bars
in a
that
bar
stand at the
screen.
inlet
Bar
of nearly
screens
every
are
wastewater
exactly
treatment
what you would
plant,
think. They
designed to
are
stop
large
larger
vertical
items from
bars
getting
that
to the
stand at
plant
the
and hurting
inlet of
machinery
nearly
like
every
pumps.
wastewater treatment
This first
plant
process
designed
where
to
bar
stop
screens are
larger items
used is
from getting to
commonly
the
referred
plant and
to
hurting
as
machinery like
pre-treatment.
pumps.
The sole
This
intention
first
of
process where
pre-treatment
bar
is to
screens
remove
are
the
used is
outliers in the
commonly
sewage and
referred
make the
to
whole
as
mixture a little
pre-treatment.
more
The sole
homogeneous or
intention of
slightly less
pre-treatment is
chunky.
to remove
Bar
the
screens
outliers in
are
the
typically
sewage and make the
mechanically
whole
raked at
mixture a
certain
little more
intervals depending
homogeneous
upon
or
the flow
slightly
rates
less
of the water
chunky.
treatment
Bar
plant,
screens
although
are
some older
typically
plants
mechanically
will still
raked
have
at
more
certain
manual
intervals depending
removal
upon flow
processes.
rates of the water
Whatever is
treatment plant,
removed
although
from
some
the bar
older
screens
plants
is
will
then
still
sent
have
off to
more
your average
manual
landfill
removal
or solid waste
processes.
handling
Whatever is
facility.
removed from the
Or,
bar
in the
screens
case
is then
of
sent off to your
unusual
average
items such
landfill
as
or solid
guns, they're
waste
sent off to
handling
the evidence
facility.
locker in a
Or,
police
in the
station to
case
be
of
investigated.
unusual items such
Next
as
up is
guns,
the
they're
grit
sent off to
chamber.
the evidence
Grit
locker
chambers
in a
are the
police
next
station to
steps in
be
the pre-treatment
investigated.
process following
Next
bar
up
screens.
is the grit
Since
chamber.
these bars
Grit
don't
chambers
catch
are the
everything,
next steps in
larger
the pre-treatment
particles called
process
grit
following
still
bar
need to be
screens.
removed from the
Since
sewage
these
as it is
bars
made
don't
even
catch
more
everything,
homogeneous. As
larger
the sewage
particles
flows
called
into
grit
the
still
grit
need to
chamber,
be
the
removed from the
velocity of the
sewage
rather
as it is
viscous
made
sewage
even
is
more
adjusted to
homogeneous.
allow for
As the
particles
sewage
of
flows
sand
into the
and
grit
rock
chamber,
to
the
settle out.
velocity of the
This
rather
is needed
viscous
because
sewage
these
is
particles
adjusted
can't
to
be
allow for
removed using
particles of
chemicals, and
sand
they could
and rock
potentially
to settle
clog or
out.
destroy
This is needed
pumps
because
later on
these
in the
particles
process.
can't be
There are
removed
three
using
types of
chemicals,
these
and they could
chambers:
potentially
horizontal
clog
grit
or destroy
chambers,
pumps
aerated
later
grit
on in the
chambers, and
process.
vortex
There are
grit
three
chambers,
types of these
which all
chambers:
accomplish the same
horizontal grit
task using
chambers,
slightly
aerated
different
grit
methods.
chambers, and
Following
vortex
the
grit
grit chambers,
chambers,
the
which
sewage
all
will move on
accomplish
to the
the same
primary
task
treatment
using
process,
slightly
which
different
starts
methods.
with a large
Following the
basin
grit
called a
chambers, the
primary
sewage will move on to the
clarifier.
primary
Primary
treatment
clarifiers
process,
and
which starts
clarifiers
with a
in
large
general
basin
function on the
called a
principle of
primary
settling
clarifier.
velocity.
Primary
This term can be
clarifiers
defined
and
simply as the
clarifiers
speed
in
at which a
general
particle
function on the
settles.
principle of
For
settling
wastewater being
velocity.
pumped into
This term can be
clarifiers, it's
defined simply
important
as
that
the
the flow
speed at
rate of
which
the
a
water
particle
being pumped
settles.
in
For wastewater
doesn't
being
exceed
pumped
the
into
settling velocity
clarifiers,
of
it's
the particles
important
trying
that the
to be
flow rate of the
removed.
water
In
being
order to
pumped
accomplish
in
this,
doesn't
engineers
exceed
will
the
vary
settling
the size
velocity
and
of the
number of
particles
primary
trying to be
clarifiers in
removed.
accordance
In
with the
order to
plant's
accomplish
permitted
this,
sewage flow
engineers
rate.
will vary the
This
size
ensures
and
that
number
at
of
varying
primary
flow
clarifiers
levels,
in
solids can settle out of primary clarifiers to the correct quantities. At this step in the process, the slightly treated wastewater, which is referred to as effluent, is free of solids larger than micrometers and should be all organic matter, which will be treated further. The top layer of the clarified water flows over a weir wall or organic matter space in the process called the aeration basin. Now begins the process of secondary treatment, the sole focus of which is to significantly degrade the biological content of the sewage. In many cases, this process starts with aeration basins. Effluent flows into the aeration basins, at the bottom of which are hundreds, if not thousands, of tiny air blowers that create bubbles through the water. The water is pumped into this tank along with something called return-activated sludge. You can think of return-activated sludge as a bunch of happy little bacteria that get to eat their favorite foods all day long. This introduction of significant amounts of bacteria along with the massive amounts of oxygen injected from the bubblers creates an environment perfect for the process of aerobic digestion. Summarized simply, it's the breakdown of organic matter along with the use of excess oxygen. Some older plants will add in another step of aeration basins referred to as oxygen.
or
Some
trickling
older
filters.
plants will add
Found
in
in many
another
older
step
plants,
before
these
aeration
filters
basins
essentially
referred
trickle
to
the
as
effluent over a
biofilters or
medium like
trickling
stone or
filters.
plastic
Found
and
in
allow
many
for a
older
film of
plants, these
bacteria to
filters
chow
essentially
down on
trickle the
any organic
effluent over
matter
a
in the
medium
water.
like
This
stone
step
or
is
plastic and
largely
allow
not
for a
used
film
in
of
newer
bacteria
plants
to
due to
chow
more
down on
efficient
any
and
organic matter
effective
in the
modern
water.
processes.
This step is
But for
largely not
plants with
used in
basins
newer
already
plants due to
installed,
more
many
efficient
still
and
use them because they
effective
only
modern
benefit the
processes.
treatment
But for
process
plants
in
with
most
basins
cases.
already
Following
installed,
aeration
many still
basins,
use
the
them because they
effluent
only
along with
benefit
much
the
of the
treatment
sludge is
process
pumped
in
into a
most
secondary
cases.
filter or
Following aeration
clarifier, where
basins,
some
the
of the sludge
effluent
is
along with
removed
much
and
of the
pumped back
sludge is
into the
pumped into
aeration
a
basins
secondary
as the
filter
return
or
activated
clarifier,
sludge.
where some of the
Further
sludge is
settling of
removed
larger
and pumped
particles
back
is
into the
also
aeration
accomplished
basins
in
as
these
the return
basins, as it
activated
is the final
sludge.
step of the
Further
process
settling
that
of
will
larger
remove
particles
solids
is
and
also
larger
accomplished
biological
in these
matter.
basins,
Water
as it
flows
is the
out of
final step
secondary
of the process
clarifiers
that will
over a
remove
nearly
solids
identical
and
weir
larger
wall to the
biological
primary
matter.
clarifiers
Water
and
flows
moves
out
on
of
to the
secondary
disinfection
clarifiers over a
process.
nearly
At this
identical weir
point,
wall to the primary
85% of all
clarifiers
organic
and moves
matter
on
is
to the
removed from the
disinfection
water, and the
process.
effluent
At this
should be
point,
safe to drink in most
85%
cases,
of all
although
organic
you
matter is
probably
removed
wouldn't want
from the
to.
water, and the
Disinfection
effluent
is the
should be
final
safe to
step of the
drink in most
process and is
cases,
usually
although you
accomplished in
probably
one of
wouldn't
three
want to.
ways, either through
Disinfection
chlorine,
is the final
ozone,
step of the
or
process and
ultraviolet
is usually
disinfection.
accomplished
Each
in one
process
of
has
three
its
ways,
benefits and
either through
drawbacks,
chlorine,
with each
ozone,
being
or
used commonly
ultraviolet
throughout the
disinfection.
wastewater
Each
treatment
process
process
has its
across the
benefits
world.
and drawbacks,
Chlorine
with
disinfects
each
the
being
water
used
through
commonly
chemical
throughout the wastewater
disinfection.
treatment
Chlorine,
process
which you
across
can
the
think of
world.
as
Chlorine
concentrated bleach,
disinfects
is
the water
added to the
through
effluent
chemical
here to kill off
disinfection.
any remaining
Chlorine, which you
bacteria
can
and
think of as
organisms still
concentrated
living in the
bleach, is
water.
added to
When
the
chlorine
effluent
is
here
added
to
to
kill
kill
off
off
any
the
remaining
bacteria, it then has to
and
be
organisms
removed
still
before it can
living
be
in the water.
discharged, as to
When
not
chlorine
kill off
is added
anything
to
in the
kill off the
discharge
bacteria,
location.
it then has to
After
be
this, the
removed
water
before it
is
can be
safe enough to
discharged, as to
discharge
not
into
kill
a
off
stream
anything in
or
the
lake.
discharge
Ozone
location.
disinfection
After
is
this, the
another
water
method of
is safe enough
disinfection
to
that involves
discharge into
pumping
a
an
stream
electrical
or
current
lake.
through the water that
Ozone
causes
disinfection
oxygen
is another
molecules,
method of
O2, to
disinfection that involves
disassociate and
pumping an
combine with
electrical
a free
current through the
oxygen
water that
molecule,
causes
forming
oxygen
O3,
molecules,
known as
O2,
ozone.
to
Ozone is an
dissociate and
incredibly
combine with
strong
a free
oxidant
oxygen
and causes
molecule,
microbe
forming
cell walls
O3,
to
known
leak,
as ozone.
rapid cell
Ozone is an
decomposition,
incredibly
and overall
strong
damage to
oxidant and
cells.
causes
In other
microbe
words,
cell
it
walls
kills
to
off
leak,
bacteria.
rapid cell
The last
decomposition,
common
and
method
overall
uses
damage to
ultraviolet
cells.
light to
In other
scramble
words, it
bacteria's
kills
DNA
off
so that they
bacteria.
cannot multiply.
The last common
In
method uses
UV
ultraviolet light
disinfection, the
to scramble
bacteria in the
bacteria's
water are
DNA so that
killed,
they
rather
cannot
they're
multiply.
sterilized,
In
rendering them
UV
harmless. If you were
disinfection,
to
the
ingest
bacteria in
water
the
with
water
living
are
microbes
killed, rather
immediately
they're
following UV
sterilized,
treatment,
rendering them
any harmful
harmless. If you
bacteria
were to
would be
ingest
unable to
water with
multiply
living
or render your
microbes
body
immediately
damaged.
following UV
Engineers
treatment,
choose
any
between
harmful
these methods
bacteria would
based
be
on a
unable to
variety of
multiply
factors
or
such
render
as
your
flow
body
rates,
damaged.
cost, and
Engineers
location of
choose between
discharge,
these
which brings
methods
us
based
to
on a
the final
variety of
step:
factors such as
effluent
flow
release.
rates, cost,
Effluent
and
release
location of
exists in one of
discharge,
two
which brings
forms.
us to the
In
final
most
step.
cases, the
Effluent
now treated
release.
water is
Effluent
released back
release
into a
exists in one
stream
of two
or lake
forms.
or other
In
water
most
source.
cases,
In rare
the now
cases,
treated water
usually
is
in
released
areas
back
where
into
water
a
is
stream
scarce,
or
the
lake
effluent
or other
discharge
water
from a
source. In
wastewater
rare
treatment plant
cases,
can be
usually in
discharged
areas where
into
water
another
is
treatment
scarce,
plant
the
directly
effluent
where it will be
discharged from
treated
a
further for
wastewater
consumption.
treatment plant
This
can
is
be
referred to
discharged
as
into
full
another
cycle
treatment
water
plant
reuse.
directly
From
where
a
it will be
chemical
treated further
perspective,
for
the final drinking
consumption.
water
This is
is the
referred to
same
as
as
full
normal
cycle
treated
water
water that flows
reuse.
through your
From a
pipes
chemical
now, but due
perspective,
to
the
the
final
connotation
drinking
of your
water
drinking
is
water
the
being
same as
sewage
normal
just days
treated water
before,
that
this
flows through
treatment
your pipes
process is
now. But
normally
due to the
shied away
connotation
from
of your
or not
drinking water
heavily
being sewage
publicized.
just
The
days
entire
before, this
process
treatment
of
process
wastewater
is normally
treatment
shied
takes on
away from
average
or not
24 to
heavily
36 hours
publicized.
from
The
when a drop of
entire
water
process of
enters to when
wastewater
it
treatment
leaves.
takes
Each
on
wastewater
average
plant will
24 to
receive a
36
permit for
hours from
flow
when a drop
rates,
of water
chemical
enters
levels,
to
and
when it
effluent
leaves.
quality,
Each
among other
wastewater plant
things,
will
from the
receive a
EPA that
permit for
outlines the
flow rates,
necessary treatment
chemical
for a
levels, and effluent quality, among other things, from the EPA that outlines the necessary treatment for a plant. Wastewater plant operators will make adjustments to a plant's operation and constantly measure levels to ensure proper discharge and proper treatment. Without these operators and the dirty job that they do around the clock, our sewage would always stay sewage and sanitation in modern cities would be much, much worse. Wastewater treatment is an essential dirty job, and you can thank the 14,748 treatment plants in the U.S. alone for not having to worry about what happens when you flush.
So this is a nice video outlining the basic principles for treating the wastewater. And that, as you can see, there are quite many familiar processes that's being used in the wastewater treatment compared to the drinking water treatment, right? We have the disinfection, we have the filtration, sedimentation, but they're using a slightly different terms there. So later on, we can find out what each term represents and what are their major mechanisms. But before we learn about these detailed water treatment processes here, we need to know what is or what are the characteristics of the wastewater. So here in this class, we're going to mainly focus on the municipal wastewater, which basically are the water that's generated from the human beings or the daily lives, right? So for these characteristics, it can be divided into the physical side and also the chemical aspects. In terms of the physical aspects, we're going to learn about, or we're going to focus on the color, the odor, temperature, density, and so on. So in terms of the color of these wastewater will typically look very dark, right? You cannot think of the wastewater that looks as clear as the drinking water there. So they will typically show a color of gray or dark gray. And they will have a very, very nasty odor. And typically they are in the temperature range between 10 to 20 Celsius. And in terms of the temperature, this average temperature is above the average temperature of the water resources, for example, the lake water or the river water, which is mainly because the wastewater is coming from that's coming from your homes or from the industry. They're typically heated. Just think of the situation where the water that's coming from your bath or the water that's coming from the power plant. Typically, they're emitted under a relatively higher temperature, which is going to raise the overall temperature of the wastewater. And in terms of the specific gravity, we mentioned that specific gravity is the density relative to the water density, right? So by having a specific gravity of 1, that means that the wastewater have a density of 1 gram per centimeter cube, which is the water density, right? This is also can be translated into 1,000 gram per liter, right? Because 1 liter is equal to 1,000 centimeter cube. And in the wastewater, not only we have the water inside, it also contains so many types of the contaminants. And the solids, so basically the solids are a major part of the pollutants that's in the wastewater. So typically in the wastewater or the municipal wastewater is going to contain around 500 milligram per liter total in terms of the solids, which is around 0.5 gram per liter. Okay, so as you can see, this solid content is really minimal or negligible compared to the mass of the water in there. So among these 500 milligram per liter of the total solids, half of them exist in particulates. So what about the other half? And typically the other half will exist in salts, for example, or the ions, sodium chloride, sodium nitrate, or carbonate, so on and so forth, right? So those will just be dissolved into the water there, while the half of the solids will exist in particulates. And for this 250 milligram per liter of the particulates, then half of them are settlable, which means that they are heavier particles. So if we give them enough residence time or settling time, these larger particles will just settle to the base of the water or of the wastewater ducts or containers. And because there are still half of the solids existing as non-settlable or they're suspended in the water, that's going to create the turbidity of the water. So basically it's quite similar to the coagulation flocculation process, right? We talked about the suspended solids in the water, which are difficult to remove. So those are the non-settlable solids that's existing in the water. And you can see that this mass concentration is around 125 milligram per liter for the municipal wastewater. And on the chemical aspect, we're going to use several parameters to describe the wastewater. So we learned in our last section about the biochemical oxygen demand. We learned about the BOD5, which is basically the BOD after 5 days of the treatment, right? The BOD5 for the municipal wastewater is around 200 milligram per liter. And also the COD. So COD is a chemical oxygen demand, right? That's the oxygen demand decided by by adding in very strong oxidizing chemicals in the water. So that is around 500 milligram per liter. So by plugging in the rate of the oxygenation, we can actually calculate what is the ultimate BOD there. And what you can find out is that the ultimate BOD will be smaller than COD. which is mainly because part of these organics are being used by the microorganisms to construct themselves, right? And they're not, and the microorganisms are not going to consume all of those organics because they're also emitting organics or that they cannot process into the water. So that is why the ultimate BOD is going to be smaller than the COD there. And therefore, there is a correlation between the BOD and the COD. And in terms of the nitrogen contents, typically we will use the total cubital nitrogen, or the TKN, to describe the nitrogen concentration in the water, in the wastewater. So these nitrogens will exist in the organic contents or organic form and also the ammonia form. And typically for the municipal wastewater, they have a TKN of around 40 milligram per liter. So we want to treat these nitrogen. On one hand, it's because these nitrogen will actually demand oxygen, right? We talk about the NBOD in our last chapter. So these will remove, or these will reduce the dissolved oxygen in the water. But at the same time, the nitrogen will exist as a nutrient, right? So they can be utilized by the algae, which is causing the algae bloom, and that will further reduce the water quality by forming a lot of biomass there. And in terms of the phosphorus can exist in the orthophosphates, polyphosphates, and organic phosphates. And we call these phosphates as the total phosphorus, or the TP. And for the municipal wastewater, they have an average concentration of around 10 milligram per liter. So this TOC here means the total organic carbon, and they normally have a concentration of around 50 milligram per liter. Okay, so these are the characteristics on the chemical side of the municipal wastewater. And the reason why we want to treat the wastewater quality is that people set up standards, right? We don't want to emit all of these wastewater into the environment, and that is causing hazards to the ecosystem. So that's why we set up these standards. And so then we need to know what are these standards briefly. And there are standards for both the federal level and also for the local level. And in terms of the federal level, they will require that the wastewater treatment will need to go through secondary treatment. Okay, so later we'll find out that for the water treatment and wastewater treatment, we have the pre-treatment process, primary treatment process, and also the secondary treatment process. And for the federal requirements, we need to do all of these. Okay, so there can be tertiary treatment, which is further higher levels of the treatment. But in terms of federal level, we need to do until secondary treatment process. Okay. So the federal level regulates that for the BOD5, you need to satisfy the monthly or weekly limits here. Okay, so for the monthly limits, it's around 30 milligram per liter, while for the weekly limit, it is 45 milligram per liter. So what that means is that if we measure the BOD5 every day, and if we average the BOD5 concentrations over a whole week, then the concentration or the BOD5 value have to be lower than 45 over a whole week, and has to be lower than 30 over the whole month. So you may wonder, why are we having different standards for the weekly or monthly requirements here? So this is actually considering the fluctuations in the emission of these BOD or these oxygen demanding materials. For example, if we plot out the emitted BOD as a function of time, so there can be a really low concentration, and there can be also high concentrations here, right? And this higher or lower concentration is not stable, or is very random, because it really depends on how people consume the water, right? So let's say that if we measure the BOD concentration over this entire week here, let's say that this is 7 days. So as long as this average concentration, which is around here, is below 45, then we'll say that, or below 45 milligram per liter, then we'll say that the water quality is good enough, because there are also lower concentrations over the rest of the month here, right? So if we look at the average concentration over the whole month, then it might look like this. Okay, so this will also satisfy 30 milligram per liter. So that's why we set up different standards for different averaging times here. So this also happens for the suspended solids, or the SAS here. So for the suspended solids, the average monthly concentration needs to be lower than 30, and the average weekly concentration needs to be lower than 45. And in terms of the pH, the federal limits regulates that the pH have to be within the range between 6 to 9. And further, in terms of the local level, people will put more stringent requirements in terms of the wastewater quality, because it really depends on what type of watershed it's going to discharge to. Because if the ecosystem in that watershed is very fragile, then we have to put on some more stringent requirements to avoid or to prevent the damage to that ecosystem. So for these local levels, we may put into more limits in terms of the water quality. For example, we will require the ammonia concentration, the total nitrogen concentration, phosphorus concentration, and even the E. coli concentration. Okay. And for these treatment plants, that's treating the water quality or the wastewater quality, they will need an operating permit. Okay. And also they will obtain those standards from the EPA as has been shown in the video there. Okay, so here I'm listing a few tables regarding the what is the typical concentrations of these contaminants in the municipal water, and also the industrial emitted water, and also what are the EPA regulations. So here is showing the first table shows the typical composition of the untreated domestic wastewater or the municipal wastewater. So actually people will use different standards or different categories to describe the wastewater quality. So we can have the weakly polluted wastewater, medium level wastewater, or strongly polluted wastewater. For different categories, they will have different concentrations of these constituents. For example, for the BOD5 or the suspended solids, you can see that mentioned that it's around 200 for the BOD5 or around 200 for the suspended solids. Those are among the medium levels here. For the weakly polluted water, they may have a lower concentration of these constituents, right? And this is the municipal wastewater. And in terms of the industrial wastewater, they will have very different concentrations of these pollutants, because it really depends on which type of industry we're talking about. Because different industries, they will process their chemicals or the resources differently, and their wastewater properties will also be quite different. For example, if we're talking about the fermentation industry, then they will typically have a very high BOD5, right? And also the suspended solid concentration will be very high too. And if we're talking about the slaughterhouse there, then the BOD5 really depends on what is the typical operating periods, right? Because they're not operating the plant under a steady state condition. And we need to talk about the demand and supply. So there's always a range in terms of these water quality here. And as you can see, for the industrial wastewater, they will have much higher concentrations of these pollutants or the constituents. So that's why we need to put in more stringent requirements for these industrial plants so that they can purify their water before they emit them, before they dump them into the nature here. Okay. So here is a table that's showing the EPA requirements in terms of the different constituents of the water. So there are conventional requirements, right, or the conventional pollutant categories, which includes the BOD5, total suspended solids, and also the oils. You can see that there are different types of the oil too, and also the pH, which we are quite interested in. And in addition, there are non-conventional pollutant categories, which is a broader spectrum of these requirements, which will include, let's say, the COD, BOD7, right? So other types of chemicals, ammonia, fluoride, manganese, so on and so forth. Okay, So you may say that, oh, the EPA is putting quite stringent standards in terms of the water quality. But look at this table here. So this is a table that's listing the EPA's priority pollutant list. Okay, so this is all the pollutants that EPA is interested in, but also this is a priority list. You can see that in this list there are 126 different types of the pollutants. So if we really want to regulate the water quality in a more stringent standard, we need to measure the concentrations of all of these pollutants so that we can make sure that wastewater is safe to dump it back into the atmosphere, dump into the environment, or it's even safe to drink. Okay. So further, this is the limit that we'll talk about, or the standards the EPA put in regarding the concentrations of these pollutants. For example, for the BOD5, it requires that the monthly concentration, or the average monthly concentration, needs to be lower than 30, while the weekly concentration needs to be lower than 45. So similarly for the suspended solids, we have similar requirements, right? And in terms of the pH, it has to be in the range between 6 to 9. And for the CBOD, or CBOD5, it has to be in the range between 25 to 40. Okay? So these are the requirements or the standards that people put on the wastewater treatment processes. So now let's look into a few examples of the wastewater treatment devices. So the first system we're going to look into is the on-site treatment system. Okay, so the on-site treatment system are different from the wastewater treatment plants, which are accommodating much more water, or much higher quantity of the water from the different industries or from the municipal sewage. So for these on-site treatment systems, they'll typically have a smaller volume, right? They can treat the water quality more efficiently, while they can only accept small quantity of water. So they're designed for homes and communities in rural areas, and actually they serve quite a large fraction of the population. So they'll serve 25% of the population, right? And the rest of them are actually served by the wastewater treatment plant. So the most important on-site treatment system is called the conventional septic tank systems. So as you can see later, these septic tanks typically will have a quite simple structure there, or quite simple mechanism there. So these conventional septic tank systems actually covers 85 to 90% of all the on-site systems, and they also have a pretty long lifetime, from 20 to 30 years. But if you use for more than 30 years, then you may have the leakage from the septic tanks, and then these leakage might cause pollution to the drinking water or the underground water, and then further affect the drinking water's quality there. So in terms of the mechanism of these septic tank, and here I'm just showing a very simple geometry here. So what happens is that the sewage or the wastewater coming from the house or coming from the community will be introduced into this inlet T here. Okay, so the inlet T basically separates the gas from the liquid here, or liquid or solid. Okay, so the liquid or solid will basically go to this first compartment, while the larger solids or the heavier particles are going to settle down, and we call these solids as the sludge. And then the liquid will basically exist above these solids here, and there also is a layer called the scum layer, which is also quite hazardous, right? And we have a liquid level somewhere around here. Okay, so then we have a piping system that's pushing this relatively cleaner or particle-free liquid into this second compartment. Okay, so because most of the solids are already removed in the first compartment, so in the second compartment, the remaining solids are going to take extra time so that they can settle down. We can also form these sludge here, but the water in the second compartment here are going to be more cleaner. So basically we use this simple, let's say a baffled system to regulate the flow of the water, and then we can get water that's with the treated quality. We're not saying that these water quality is good enough for drinking, but at least they're removed, or their concentrations of the contaminants, especially for the solid particles, is much lower now. So then after these water are being treated, they will be delivered from the outlet and then to a drain field. So here it is showing how the drain field works. So basically the wastewater is being treated by the septic tank, and then these treated water will just go through these rocks or sand formations, right? So we know that the contaminants in the water, when they are in the solids or in the sands, there will be a retardation coefficient. So basically those contaminants will flow with a slower speed there, all right? And also the speed here is very slow. We find that if two houses are separated by 100 meters, which is an example problem we talked about earlier, they're separated by 100 meters, then it takes almost 1 year for the contaminant to move from the house A to house B, right? So basically from these sand filtrations or rock formations here, the water will get further purified, and then the water can finally mix with the groundwater. But we may still quite concerned about the contamination of the groundwater source, because we're using this groundwater as the drinking water here, okay? So therefore we have to revise these septic tank systems, right? So we can have the septic tank systems with modifications. So what we can do is that we can enhance the aeration. So if we enhance aeration, what that means is we're going to introduce air in here, so generate a lot of bubbles here. So if we have enough oxygen, then the microorganisms in these wastewater are going to oxidize the organics or the organic components in the water, so that we can remove or we can lower the BOD in the treated water, right? So we can reduce the BOD in the tank. And what we can also use is a system called the recirculating sand filter system. So this is quite similar to the idea compared to the drinking water system, drinking water treatment system, right? So basically we have these sand filters here, and then what we do is that after the water is being treated by the septic tank, they will be introduced into these pipes here, and the pipes have small pinholes, right? So the water are going to basically get emitted from these holes and then get filtered from these sand filters, okay? And then by this way we can remove the contaminants and basically leave them in the sand filters, and then further we can collect them by this pipe here and then later introduce them into the drain field. So basically this process uses the sand filtration to further remove the suspended solids and also some organic components or the chemicals from the water through the process called the adsorption, okay? So there's another mechanism that's called the constructive wetland systems. So what happens is that after the water is being treated by the septic tank, they'll be introduced into two compartments of the wetlands. So for the first part of the wetland, they are composed of this impermeable layer. So what happens is the water is not going to get transported further lower down there. So the only way the water can flow is horizontally through the wetland, okay? So in this way, the water can get filtered, and then at the same time while they are being filtered, they leave those organics or the nitrogen, phosphorus in the soil or in the sand, and then these are the nutrients for the plants or for the organisms that's living on this wetland, okay? So then after the water is being filtered, they will be introduced into the second part of the wetland. And further, for this part of the wetland, they will have the permeable layer where the water can further diffuse or settle down into further the groundwater. But still we're able to collect some of the water from the second part of the wetland, and then they can exit from here, okay? So apart from these systems, there's also a system called the Baffled Bioreactor system, or the BBR. This is also quite widely used, especially for the military use, because in military, when they move to different locations, they want to avoid the contamination of their drinking water source from the wastewater, right? So we have to make a very condensed system where it can sit just above the ground, because if you look at the septic tank, they typically exist pretty below the land surface, right? Because water have to use its gravity to go into these tanks here. But for these baffled bioreactors, they can just sit outside and then just above the ground. And then it is also a pretty condensed system where you can treat the water quality quite efficiently. So what happens in this baffled bioreactor here is that we'll introduce the wastewater first by through this anoxic chamber. Okay, so what happens in the anoxic chamber is that we're achieving the denitrification, which is converting the nitrate into ammonia, or the ammonium ions. Okay, so by doing this, we can further enhance the oxidation process of these nitrogen species. Okay, so basically after they are being treated, they will be introduced into this aeration zone here. So inside the aeration zone, we're bubbling oxygen or air in the water. So this is, on one hand, is oxidizing the organics in the water, right? On the other hand, it's also oxidizing these ammonium in the water. So at the same time, the larger particles are going to settle down to the base, and then we're going to obtain relatively cleaner water from the top here. And then by these baffles or channels here, they'll further flow by, so to give them a longer residence time so that particles can settle down. And then we're able to basically get cleaner water from these different channels. So you can see that it needs a relatively longer residence time in order to remove these contaminants from the water, right? So in this way, we can also treat the water quality. So how do we make sure that the water quality is good enough, right? How do we make sure that it satisfies the standards established by the EPA? So what we do is that we'll typically measure the water quality, or for example, the BOD5, suspended solids, and nitrogen after some time. Okay, for example, this is measuring the wastewater quality for every 2 weeks. So you can see that there is indeed some fluctuations, because it really depends on what are the supplies and demand, right? Maybe for some time period, there is more emission, or there's some activities going on in the industry or at someone's home, so that the water coming from that event is more polluted. Okay, but if we take the average of all of these constituents and try to find out what are the average values, then we can compare that against the EPA standard there. We can further tell whether they satisfy the requirements or not. Okay, so this is all about the on-site wastewater treatment systems. So there are larger scales of the wastewater treatment plants, which is the municipal wastewater treatment systems. Okay, so they will be composed of more detailed procedures. For example, we have to remove the large debris by the screening method. We have to remove the grit, which is basically the larger particles, and by a device called the grit chamber. And as you can see from the video, there are 3 different types of the grit chambers. For the heavier solids, we'll use the primary clarifier to remove these particles. And in terms of the dissolved organic pollutants, or the BOD, or the nutrients, we're going to use the biological treatment. Okay, and for the microorganisms in the effluent, we'll use the disinfection. So here, we're going to go through the treatment process, which is similar to the contents shown in the video here, but it's shown in this graph here. So after the wastewater are being collected, we call them as raw sewage. So they will go through the screens, okay, or the bars, right, to remove these larger debris or larger chunks of the solids. So here is showing a new device that's called the comminutor, right? So what the comminutor does is basically break down the larger particles into small pieces, okay? But I don't think in our textbook we covered this device here. So basically it's converting these larger particles or tearing these larger particles into smaller suspended particles or the grits, okay? So then the water will be introduced into this grit chamber where these larger particles are going to get removed, and then they will go into they're going to introduce into the primary clarifier, right? So the particles will further settle down, right? And then the cleaner water will go to an aeration tank. So inside the aeration tank, we're bubbling a lot of air, right, to maximize the oxidation of the organic components in the water to lower the BOD values. So after we get these cleaner water, they'll go to this secondary clarifier. And inside the secondary clarifier, what settles down here, we need to pay attention, will be largely composed of the microorganisms, right? We need these microorganisms to maximize the oxidation process in this aeration tank. So that's why we also call this constituents as the activated sludge. And what we do is that we will take a part of these activated sludge back into the aeration tank, right? So as the video shows, so these are basically the microorganisms or bacteria that can eat unlimited food, right? So they are always consuming these organics in the water by using these recirculation process here. So after we get these further cleaner water, we can use the disinfection to remove the microorganisms. We can either discharge them or send them to a tertiary treatment, right? So one thing we need to note is that, so here, although we're separating this entire process as a primary treatment and secondary treatment, but inside the primary treatment, people will also categorize these three processes as the pre-treatment. So this really depends on the definition of the treatment processes. According to our textbook, these processes are called the pre-treatment, while the primary treatment is just this primary clarifier here, while the secondary treatment will include these aeration tank, secondary clarifier, and also these activated sludge process. Okay. So as you can see from these processes, one thing that's quite different from the drinking water system is that we need to involve this sludge disposal, right? So the wastewater contains a lot of solids inside the wastewater, right? So we have to remove these sludge from the wastewater. So a serious process is being used to dispose these sludge. So we have to first thicken the sludge here, which is basically to make it more condensed or concentrated. And then we need to go through the stabilization, dewatering, and finally it's the final disposal. Okay, so they can be used as fertilizers, or they can just go to the incinerators to go through the combustion, or they can just go to the landfill. And in terms of the pre-treatment of the industrial waters, again, this really depends on the definition of different treatment processes. So the wastewater treatment plant will also adjust the pH or remove some of the organic matter or the toxic material removal, right? So we're trying to do these to avoid the damage to the other parts of the wastewater treatment system, right? For example, if the pH is too low there, then what that means is that the wastewater is too acidic, then that might corrode these parts or ducts in these in the wastewater treatment plant. So we have to adjust the pH before they're being introduced into these different parts. So specifically on the wastewater treatment, the EPA created a program called the NPDES program, which is short for the National Pollutant Discharge Elimination System, right? So you can find more information from there. So that's all for the contents of this class. So let's try to review what we have learned here. So we learned about what are the physical and chemical characteristics of the municipal wastewater. What is TKN? This is a value that's regulating or describing the concentration of the nitrogen-containing species. For example, what are the major components of the conventional septic system? It is a relatively simple system, right? So we're basically separating the wastewater into gas, liquid, and solid, right? And what is a typical treatment process for the wastewater, and how do we handle the wastewater sludge? So that's all for the contents of this class, and